So we have with us today Dr. DK Kang. Dr. Kang is one of our assistant professors here at the UBRP. He obtained his PhD at the Korea Advanced Institute of Science and Technology in 2006. And then after that, he promptly went to Harvard Medical School, where he had a variety of positions. He worked as a research fellow, and then as an instructor, and then as an assistant professor of dermatology. And then we were very lucky to have Dr. Kang come here in 2017, where he now serves as an assistant professor in biomedical engineering, as well as optical sciences. His research here, I'm really excited to hear about. He does some really interesting work with medical imaging and small, or I should say portable, affordable devices. Like, I remember you developing a portable device for detecting corneal ulcers, and he's developed some technology for smartphone microscopy, and some other very interesting things. And so, as you can see today, we're going to be looking at skin cells. So please help me give a warm welcome to Dr.
So yeah, good to see you guys. That was one of the best introductions I ever heard. So thank you. So as introduced, I go by DK. My Korean name is Dongkyun. People just butcher it typically, so I go by DK. It can be not a big fruit king, dancing king, not impossible. I like it. So for the first 20 minutes or so, I'm going to talk about what I do for research, which is in vivo microscopy. It's always fascinating to me, being able to look at your cells directly from your skin without having to cut it. It's always fascinating. So I'm going to talk about that for the first 15 to 20 minutes ish. And after that, for the second part of my talk, I'm going to talk about my journey, how I ended up here, right? Jeez, right? So that's what I'm going to talk about. So hopefully, I keep you guys entertained. So that's what I'm looking forward to. In terms of research, part of the talk I had to disclose my financial conflict of interest, which really is boring for many. So I'm going to move on. Well, we all live in Tucson, and we have beautiful 300 days of sunshine, right? Are we excited about it? No, not excited. It's just too much. I'm looking. This is not really part of higher. But so sunshine is good, but at the same time we have challenges, right? So we get to hear a lot about sun protection, how we always have to put sunscreen on when you're outside, and so sunshine and UV exposure, it tends to lead to some of the skin cancers, things like the basal cell carcinoma, squamous cell carcinoma, melanoma, or Merkel cell cancer. So there are these many skin cancers, and as you might have heard before, skin cancer is the most common cancer, period. And basal cell carcinoma is the most common cancer, period. So that's what it is. So what happens if you have this tiny little thing, something popped up, what do you do about it? You go see a doctor, and your dermatologist takes a look, I don't know, man. So they take the tissue out through a process called punch biopsy. Have you ever heard of this, or have you ever gone through this? Okay, so some of you, okay. So this is where you have this very sharp cylinder or hollow core that you introduce into your skin and go in and twist out, right? So then the tissue comes out as this ice cream cone shaped tissue. You snip it, okay. And once you take the tissue out, you fix it, embed it in the formal paraffin, section it, and eventually the end product is this. You have this slide glass. You have this thin section of tissue sitting on it with some staining. And once we have this, a pathologist takes a look at it under a microscope and tries to figure out if there is cellular features that are known to be associated with skin cancer. Right? So for instance, everyone knows what this is, right? What is this disease? Come on. No? So this is not pathology 101, right? So this is basal cell carcinoma. It should be very like uniform layer of epidermis, which is the very, very top layer of the skin. And underneath there should be dermis. And suddenly, when the person has basal cell carcinoma, there's this big tumor. Okay. So if the pathologist sees this, then that's diagnosed as basal cell carcinoma. Then the patient goes through treatment. Okay. So that's how it happens in the US. But in places like Uganda, so this is a picture that was taken from my Ugandan trip. And this is a picture of one of the few pathology labs in the country. And this is what we're seeing over there. Okay. So can anyone guess what this Coca-Cola people is doing in the pathology lab? Can anyone guess? They're drinking Coca-Cola. And there's like mineral water. What is this? What's that thing?
For storage.
Yeah, sure, yeah. So right, exactly. So there are not that many pathology labs in the entire nation, right? So they have to collect tissue through excision or biopsy, right? But then they have to transport it into the central facility. But there's such a shortage of supplies and standard, containers and so on. They have to use whatever is available. So this is really showing the challenges that we are seeing in low and middle income countries or low resource areas. Okay. So how about we just take a look at the skin directly with microscope, right? So if we can if I go back, two slides back, basically cellular details, cellular structure, that's what people are using, right? And we know what we can use to take a look at cellular structures. Microscope, right? So why don't we just use microscope to take a look at your skin directly, right? So that's one thinking. If you do that, what you're gonna see is something like this. Okay, you kind of see nice sort of surface roughness, up and down, such as our life, So this is like what you get to see with microscope. And why is that? So why don't we see like beautiful cells and stuff? Because we don't have cells. We don't have cells, right? So what happens is that skin has layers, right? Or any human tissue has layers. That's what you're seeing here. So for instance, if you want to take a look at this particular cell or cell layer at a given time, you try to focus your light on it, but what actually happens is that the light goes everywhere. Okay, so that makes it really challenging because the image that you're seeing is not only coming from here, but it's coming from all this big volume of tissue. So everything is kind of smeared and blurred, so you don't get to see what's actually inside the cellular structure. Does it make sense? Yeah, hopefully it makes sense. You guys know about microscopes, right? Right. Just trying to make sure. So there's this particular type of microscope, confocal microscope. Has anyone heard of this confocal microscope? Yeah, good. Okay. So this has become such a standard for biology or chemistry research. So some of you might have heard of it, might have used it. This is a technology where we use a laser and focus the light into a tiny little spot and detect the light that's coming from that tiny little spot only. So basically, there's this pinhole right at the detector that rejects any signal. Oh, sorry, I have to pick up my kid. Yeah, that's right. But so today was the last day of his school. He got picked up by my wife, so he's not stranded. So. But basically, we have to compromise. What it does is that it lets you take a look at very thin layer of the tissue at a time. So that's the only thing that you have to do. You don't have to. So there are commercial confocal microscope devices that's already available. And what you can do with these commercial devices is that you can take a look at skin and tell if the skin is normal, which is what you're seeing on the left, or like something like melanoma. So there's the clear structural change between normal versus cancer. Okay? And we don't have to take the tissue out. That's beautiful, right? We just take a look at it and make this. And this can be particularly helpful in places like Uganda, where they don't have, resources for making story slides. Now, this is fantastic, but the problem is that the device cost is like $100,000. Okay, so even in the US, there are only like 63 hospitals that have one of these devices. In Arizona, guess how many we have? How many? Zero? No, two. So UBRP has one in the dermatology service, and then there's another one in Phoenix at Mayo Clinic. So we have two. Okay, so that's better than national average, right? So oftentimes the dermatologist has to, make a decision whether to buy the Lamborghini or a microscope. Right? So that's a situation. So what we do differently in my lab is that the traditional way of doing this confocal microscope is, has anyone been to laser show? Like, kind of making nerds. Okay, so but that's okay. I'm very proud to be nerds. And so what happens is that you have a laser light, right? And then there's a scanner. It's sort of motor, very high-speed motor, and then you have this mirror. You're scanning the beam to generate certain pattern. And that same technology is being used for confocal microscope. Okay? Now, in confocal microscope, it tends to be more expensive than this kind of fancy toy laser scanner. So that tends to drive the cost up. And what we do differently is that we do this illumination with just one line. And we use something called diffraction grating. That's like a prism. You know what prism is. We might not know what grating is, but prism, what prism does is that it separates color differently, right? So we can do the same with this element called diffraction grating, and we send different colors to different locations. And by doing so, we can cover the entire area of the tissue without having to scan. So that's just too much, right? So that's now the program. So this is the first prototype that we made, and this is using a smartphone camera to collect confocal microscopy data, which is great. And we actually made custom folders for optical components using the SolidWorks. And SolidWorks, some of you might have used SolidWorks and then 3D printing. So that's how we make the microscope here. Nice, right? And it's about like 1 kilogram. The cost was $4,000, $4,200. Okay. Now we're talking about Honda Civic used in 2010. So it's not Lamborghini, okay? So it's affordable. The question is, you can put things together, but does it actually work, right? So this is what I call a selfie you can see. Okay? So this is my skin with several structures. Okay. So these are the images that you can get from our smartphone-based microscope. What you're seeing is that these are something called keratinocytes. These are the cells that constitute the epidermis, and you get to see the change of the cell and other structures. Okay. Now, what we did with this device was that we flew out to Uganda, started imaging patients with something called carpal sarcoma. It's not really a common disease in the United States anymore, but it still is one of the most prevalent cancers in Uganda. Okay. So with my collaborators there, we imaged patients in vivo directly, or then taking the tissue out and then take a look at the tissue right at the spot. And we were able to see some of the interesting structures, such as dark openings here and there, which might be associated with the capillaries that are related to the cancer. So that's one. We also improved the device. This is second generation device in collaboration with Dr. Clara Cruel. She's the Skin Cancer Institute director at the U of A. So from this collaboration, we made second generation device. And with that, we were able to image most of the common skin cancer, which is basal cell carcinoma, with our device, which is $5,000 Honda Civic, used 2010, right? Lamborghini device over here, right? So basically, what you're seeing is that you're seeing tumor islands of the basal cell carcinoma in both devices. You get to see this convoluted blood vessels in both devices, right? I admit that the Lamborghini device still works better in terms of image quality, but the key structures that we need to find or we need to visualize, we are able to do so. Right? So this is really excellent, exciting. The other thing that we can also do is to do very fast imaging. It's might not make too much kind of interesting to you guys, but this one, what you're seeing is that there's this red blood cell flowing on my lower lip capillary, and this device is so fast that you can take a look at flowing blood cells very nicely. Okay? So if one of these blood cells were deformed in a certain way, then we would be able to detect that, and that can be useful for something like sickle cell disease diagnosis. Okay. We also have developed something called a smartphone comparable endoscope. So we made an endoscope that's about the size of pinky in terms of diameter, and this is like 10 millimeter diameter and probably foot long for the entire length. And the application here was to image the cervical precancer in Uganda. And again, the device cost was only like $1,500 or something like that. And another nice thing about this project was that we developed our own smartphone app interface of Android. I hate Android. I'm like Apple crazy, but in terms of developing your own software, Android is so much better, right? Android is good. Okay, so so basically we made our own app and we collect the confocal microscope data coming out of this kind of little device into smartphone and display. So what you're seeing is the cell nuclei directly from the tissue. Okay. So again, like you're seeing like the cell nuclei and so on. So that's pretty much about it for my research portion of it. So I kind of intended to do so. I can go over like another 20 minutes. You can switch here. So any questions about the research bit? Or we can talk about it later. Any question? Any burning question you just have to ask now? No? Yeah.
How many devices have you made so far? Have they like made?
How many
devices have you made?
Oh, yeah, sure, yeah. That's a good question. So for the smartphone confocal device, we have made like 3 devices. We delivered 2 to Uganda. So that, and then we have made even better devices. So altogether, I would say like 6, 7 devices. And as I said, like what's really nice here is that we are making our own custom folders in-house, or not in my house, but in the lab. So, and then we design something and then print it overnight and then put this together. So we can put the microscope together within a week or so. Or so I say, but my student might say, like, yeah, it takes a month. Right? Okay. So, yeah. So, any other questions? Yeah.
Are you planning to commercialize the product?
Excellent question. Yes. So there is a startup company in California, and they are, they signed an agreement with the University of Arizona to commercialize the device, and so hopefully in like 2-3 years down the road, we might be able to buy it from Amazon. $19.99 before tax, but after tax it's over $2,000 or something. So, okay. Good. All right. And so I mean, we can ask more questions later. So I want to talk a little bit about how I ended up here. How many of you are freshmen? Okay. And sophomore? Okay, juniors? Do you have seniors? Okay, you do. So it's about equal distribution between freshmen, sophomore, junior, and a little bit less than seniors. Okay, so you're all over the spectrum. Who thinks that you're gonna become a professor in 20 years? Who thinks that you're gonna? Yeah, good. That's good. Okay. Who's more interested in industry? Like making a whole lot of money. Who like making money? Okay, all right, good. That's great. So obviously, some of you don't care about making money. So that's okay. It's your philosophy. Now I have another question. Who inspired me to become an engineer? Between A, B, C. Okay. Who thinks it's A? All right. Who are these guys? Okay. No. Well, obviously it's not BTS, okay? It was not. Who are these guys? Okay, so you're so young. Okay. I feel really old. This is New Kids on the Block. Very famous. Like, I don't actually know. So they're super popular when I was young in Korea. So anyway, but they didn't encourage me to become a teacher. That's obvious. We know Beatles are the Beatles, right? See? Edison, yes, Thomas Edison, yes, thank you. Yeah. And this person, I mean, many of you chose the D because he's Asian guy. So this is my dad. He was an electrical engineer. He worked for LG Electronics for 25 years, right? So for me, like weekend activity was that my dad. I mean, so unlike here, or unlike now, even in Korea, back in the days, he had to work for 6 days a week, and then Sunday was his only off day. And I think maybe he takes like a couple of hours of nap and then just wakes up and just has to open something, right? And he just has to open his TV and then fix it, even though there's nothing to fix. And then suddenly, like our neighbors are coming with their like electronic appliances, and then like, there's a problem, can you fix it? So I get to see like pretty much every week, him fixing something like soldering a circuit board and things like that. So they really affected me a lot. Did I feel like it's cool? I don't know, but I definitely got exposed to those things. So that's what I said, and I enjoy like robot movies a lot. This is like one of the like favorite, for like popular movies back in the day. And when I was young, the dream job, the top 3 dream jobs for my generation was that the first one was president, just close to become president, and then scientist, and then military general. The 3 that were super popular. So obviously I chose one in the military side. Right? So I went to high school very focused on science and math, and I felt like I'm so talented for math. I'm this math person. Jeez, I'm this math guy, right? So I joined this math club, and 1 month in, the math teacher came to me. I don't think you have talent for this. Do something else, right? It was really harsh, I was in the point of like sort of teenage, whatever, and I was speechless, right? So then, and then this physics teacher came along and said, hey, dude, do you want to try physics? Physics is cool. So I said, yeah, yes, sir, and I want to do it because obviously I'm not good at math. So then what happened was that I won the first place for national physics competition in Korea that year. So that really changed my life quite a bit. So I gathered a lot of this confidence, so that's kind of good. And then this was like, I can see this one. And then I went to this college called KAIST, Korea University Institute of Science and Technology. It's good university. It's good university. So I studied really hard, and I had pretty good grades. Who has good grades here? Some of you. Good. That's fine. But what I'm trying to say about myself is that I was really good at grades, right? But I was really bad at actually understanding what the lecture material was. I was good at solving problems, right? So I was really bad at hands-on stuff, okay? And I was not really interested in making stuff. I was not interested in research. I was only enjoying time of my life and solving equations. Such a good. So then I went to graduate school. And why did I go to graduate school? The first reason is half of my friends decided to go to graduate school. So yeah, why not? I'm just along. And other thing was that I was afraid of getting out of school and start looking for industry jobs. So that was really anxiety provoking and there. And I didn't know why, but I feel like I wanted to become a professor at some point in my life, okay? Hey, here I am. So, And I didn't, but still, I didn't really care about research, okay? I didn't care about it, okay? And I didn't have any passion, like, I want to save the world, damn it. No, there's no such thing, okay? I just like, becoming a professor, okay? So for my PhD research, I did some stuff in high resolution optical microscope. I even started my own company with my friends. The company still exists. I didn't make any single dime out of this company, but the company still exists. And I spent like a whole year, working with my friends for the company, and that was really exciting. So that was exciting in the sense that I can now tell you guys or anyone that it was exciting, but that I hated it because there was time where for a whole week I couldn't go home. I just stay on, fixing the last minute problem to make the very first product from the company. And the first product, the first microscope that we made was sold to this Taiwanese company. So we kind of shipped it out and everything. So that was all exciting, but yes, okay. At the time, I didn't quite like it. So anyway, so that was exciting, but the company didn't make anything new. Basically, we were sort of kind of repeating what other people already have done in the US, in Germany, just making cheaper, maybe, not anything new. Okay. Then I started my job at Biomedical school, and this is one lesson that I wanna tell you or share with you, which is that whenever there's a free lunch, show up. Okay. So I went to this optics conference called Photonics West, and then there's this sign up sheet for lunch with expert lunchman, and this is a free lunch for graduate students meeting with senior professors in the field. So I signed up, right, and then I happened to sit right next to Dr. Gary Tierney. He's a professor at Harvard Medical School. We took a research, and he's like, yeah, you seem like the right person. So once you're done with your PhD, apply for a job at my lab. So that's how it happened. So lesson one. Free lunch, always sign up. Free lunch, okay? Very important. And then, so I started my job at Harvard Medical School, and there's this place called Wellman Center for Photomedicine. This is one of the best places in the world in terms of doing laser-related stuff, imaging-related stuff for biomedical applications. Okay? So I made I'm not going to much about this, but I made this hair-thin microscope, like the smallest microscope, endoscope ever in the human history. So that's one. And then the other thing was I made this swallowable microscope that can take a look at your cells as it goes down. So basically, whatever I did, I felt like I was making something useful. Okay. But still, my goal there in my first job was that I just want to publish some nice papers and then get a job back in Korea in 2-3 years. That didn't happen. So what happened instead was that my Korean friends in the same institution, they started getting jobs, really nice jobs in Korea. And it might be true in the US as well, but if the university hires someone from a particular institution, it's very unlikely that they're going to hire another person from the same institution because they want to diversify the research. Right? So I felt like my window of opportunity wasn't closing. Okay. So then this is me, or my way, Google. It's not me, but my way. So my thought at the time was that I used to be doing really well. And what happened? Is my career over? We are able to become a professor somewhere. Should I get a job in the industry? Am I unlucky? What's going on? This is all based on the mindset that I'm the center of the universe because I'm not. So that's what happened. And so I told my mentor, Gary Tierney, that I wanted to start my own project, writing the grants and stuff. And he told me, so what do you want to work on? So I get that you want to start your own sort of research or whatever. What do you want to work on? And I was like, I don't know. So then the problem, I was able to find what the fundamental problem was with me, right? Which was that I didn't have passion. I didn't care too much about research. I wanted to become a professor just because, I don't know, because they have been professor. You like somebody like professor. So I mean, I guess until that point, right? Until the point he asked me that question, I felt like I never really seriously thought about what I wanted to do in my life in terms of research, right? So that's that. And then I started to wonder how other people come to have their passion about their research, right? Some of you might already have some passion about research because your close family member went through some issues, healthcare wise. Other people might be just fascinated about something else, right? But me, no, I was not. I was not fascinated by anything. Okay? So I started asking around, okay? And so this is Dr. Smith, she's a professor and Biomedical school again, and she's my closest friend. And for her, it was very obvious from day one at Harvard Medical School that she wanted to work on biomechanics. So using optical imaging to do biomechanical study. So it was really clear for her. I have another friend, Dr. Maria Suder. She's also a professor at Harvard Medical School. And she was also very clear about her dream and passion. She always wanted to develop optical imaging technologies for pulmonary applications, so imaging in airway and trachea and things like that, right? But on the other hand, Dr. Dennis Brown, who was my mentor at Harvard Medical School, well, I came to work on kidney only because my boss asked me to do so. Okay, so sometimes it can be that you stumble upon an opportunity to work on a problem, and that problem might not go on you. So I guess my message here is that even if you don't have clear idea about what you want to do in terms of your research or career, that's okay. That's okay. Look at this guy, zero idea until he's 30 something. Okay, so it's okay. It can happen. Okay. So what did I do? Well, I get to think about what I like. Okay, so I like to make something new and interesting. And eventually, I really want to make something that's useful for people, that can actually help people, right? So, I mean, it's as simple as that. I mean, so then from there, I kind of sort of gather my thoughts together, put my grant application, and eventually I got promoted as an assistant professor at Harvard Medical School. People started to recognize me as an expert in my tiny little field. And there's this this big field, optics, small field, biomedical optics. It's a small field that I consider as an expert. Okay? So other thing that I want to say was that there was this feeling every day that research was so exciting that I parked my car at North Station Garage in Boston and then kind of walked like 15 minutes to the lab. And as I was thinking of what I was going to do that day, whatever I do today, it's going to be the first time in the world, the first time in human history, just to put like that kind of big picture around it. I mean, that's really helped me a lot. So that's that. So I guess before I wrap up, I want to say what I want to say is that when you sort of see a person like me who's a professor in a good university, you might wonder like, yeah, you kind of sort of you're like you're smart, you worked hard, and you kind of went there, right? My path was not quite like that. I mean, I got frustrated a lot and then went up and so on, right? So for anything in your life, be it like a career, a job, money, love, marriage, whatever, the reality is not really straight from here to there, A to B, right? It's more like this, right? It's more like this. That's what actually happens. And what I want to say is that you should be able to enjoy the path, not the goal, right? So I often ask my students during my course. This is my kid, back in the days when he still talked to me. I was 12 years old. I mean, so you've been to 12-year-old, right? So yeah, you start talking. So this is time that we it was one day Christmas when we bought this. You guys know what this is, right? Sandcrawler, yeah. So Sandcrawler, Lego set, beautiful. So we bought it, we put it together, spent whole days putting it together. And so if you have a chance to buy this, would you buy this Lego set assembled like that or unassembled? Assembled, yes, assembled, right? Yes, probably. So if you want to buy this as an unassembled bricks, so that you need to actually put your labor and time to make an end product, right? Why are you buying it with your money? It's the experience that you're buying, right? So the path and the experience is more important in many cases than the goal. Okay, that's what I want to say. The other thing that I want to say is that you don't want to compare yourself with others, right? I mean, that's what I did or not. And you guys live in the US, but you know, back in where I was from, in Korea, like it's very common because you know the person right next to you is right here, not there. Right? It's very easy to what other people are doing. You get to compare a lot. They're almost in a sense like it's invisible ladder that you have to climb at a certain age of your life. And if you kind of miss any of the steps, then you feel like you're a loser. So don't compare yourself to others. You have your own timing. And the other secret that I found was that you are not the center of the universe. Did you know that? Did you know that? It took me some time, okay? So my point is that there are million and one things that are out of your control. So if you do your part, but if it doesn't go the way that you want it to go, then it's not your fault, right? It's the universe's fault. Yeah, okay. And then don't get frustrated if things don't happen. So my friend Dr. Jung, he's a professor in Korea, but he gave me this really interesting example. So getting a faculty position is like find a parking space on Black Friday. Okay, even if you drive a BMW, that doesn't guarantee a parking spot, right? Even if you get into the parking lot earlier, that doesn't get you a parking spot. You just have to be lucky to some degree. Right? So I guess really good example of what's actually happening. Right? So with that, I would like to go back to research a little bit. I would like to thank my students, collaborators, mentors, and funding agencies and whatnot. And if you have any more questions, you can send me an email. I finally became Googleable. So if you do DK Kang, there's this other guy who's really good at golf. But, that's not me. So if you have any questions, send me an email. Okay, thank you. Yeah, any questions?
Were the smartphone cameras that you use like were they just ordinary smartphones?
Yeah, sure. Yeah.
I don't know, they just look so good to me. Like, it's crazy.
It is so good, right? Thank you. Yeah, so it's in the regular smartphone camera that we have used as a sensor to capture the confocal microscope data. So yes. Yeah, I mean, you guys have really nice camera in your pocket. Problem these days is that you have more than like one camera. So you have like 2-3 cameras on the back. So one of the courses that I'm teaching in optics is Opti 630. And in there we do smartphone-based, like know your smartphone, that's the homework, and then you gotta do some microscopic imaging with your smartphone, but then it's getting more challenging because now you have like 4 cameras that you have to deal with, right? So suddenly like this camera activates and that camera activates. So it's very challenging. Okay.
How did you get from Harvard to here?
Oh, so it took me 8 days. Is that what you 3,000 miles, 8-day road trip. That was fantastic. I can do it again. But yeah, so my one of my friends, from Harvard actually, she's a professor at optical sciences, and like in a couple of days before Christmas, she sent me an email like, we're hiring. Is there anyone interested? And I'm like, I'm interested, and then I just applied, and then we went through the process and got the job. And 8 days later, I'm here. Yes. Yes.
You might have already mentioned it, but I guess what's the main difference between the 2 really expensive confocal like the microscopes in Arizona that you mentioned, and then the ones that you've been making?
Right. So basically the main thing is the cost. They're like $100,000, and then we're trying to make it currently at $5,000, but then with the company that I'm working with, their goal is to make it about like $2,000. Again, as I said, $1,999.99. So if the question was more about like what's inside, that might be different. So with the commercial device, they're using laser. So you kind of have to look at one point at a time, and you have to scan that point really fast. And the optomechanical components that go with that, scanning method, that they tend to be expensive. That's one. The other thing too is that now you're looking at data one point at a time. So your data is streaming to your computer, and so you have to digitize it really fast, and then convert that into two-dimensional data, which also requires some fast, rather expensive data acquisition card. So in our case, we're utilizing the fact that we have very nice smartphone sensor in our pocket, and yeah, so that's the main thing. I mean, I can also talk about Nike sampling, Fourier transform. Nobody cares about it. Okay. It can work with other cancers too, yes. I mean, that's exactly right. So many of the cancers start from very superficial portion of the tissue because that's where cell division happens, right? So when cell division happens, there's a chance of mutation and so on. So if there is known or recognizable feature that we can visualize with our microscope, we can definitely look at it. So one of the projects that I used to work on back in Harvard was looking at esophageal cancer. So that's another thing. You just have to look at an endoscope. Oral cancer is another thing that people look at. Cervical cancer. My lab in the has a project on anal cancer. That's another one. And then we recently got rather big funding from NIH to look at corneal cancer. So anything you can image with microscope is something that you can go after. There are no questions. Any other questions? We have 2 more minutes.
How deep can your camera visualize?
Right. So the microscope typically is limited in terms of imaging depth about 150 to 250 micron. So in terms of skin, epidermis is somewhere between 50 to 100 microns. So you can image epidermis very nicely. Dermis, as you try to go deeper, it gets challenging. Something like the cornea is more doable because, as we know, cornea is pretty transparent, right? So you can go deeper all throughout the cornea. So it a little bit depends on what tissue you're looking at. Back there. No, nobody raised that. Sorry.
How different is this all that stuff compared to the commercial one?
Yeah, we haven't actually started doing proper clinical study with large population. One reason is that we're still finding that there are things that we need to improve in terms of technology. So we're kind of getting close to getting all the funding from NIH to make it faster and more portable, better quality. So once we actually get to the point that we have to do more proper study to establish sensitivity and specificity. So that's very important because as an optical engineer, we tend to make something and they're like, this works, this is awesome, but then nobody believes you, right? So we have to show that through a proper anything else? I have, other like, I don't know, I mean, I have some dancing, video. We can talk about that. Anything else? All right.
All right, thank you so
All
much.
right.